But we do have a live demo that hopefully will work. So let's just get that out. You can see that it's actually a web-based one. So we didn't want to deal with JavaFX either. And if you press begin search, so each one of these is a node that we've actually searched. And you can see that I haven't done the optimal schedule. The plan is to have a Gantt chart here. But then you can see some metrics at the top, like schedules processed, partial schedules. Each one of these, you can see how it like branches out in the state space. So I found that was really cool. And this is also completely deterministic. So this kind of gives you a fingerprint of this specific like schedule. So yeah, that's where we are so far. Some stuff to do, but yeah.
So what you saw there was a much more nervous version of me presenting a work-in-progress version of the application to the entire class. Now in this section, I'd like to tell you a bit more about some of the technical details behind how the visualization works. So in the team, I was responsible for the visualization and also the parallelization, but I won't be sharing how the parallelization worked because explaining that would require explaining how the rest of the project worked, which would in turn break academic integrity. So if you're a sneaky part 3 watching this, I'm sorry to disappoint you. So the visualizer was unique in that it was actually built with web tools. Because our solver had to be written in Java, many other groups stuck to doing theirs with JavaFX. But using web meant I was much more confident in being able to pivot away from like risky ideas that were cool, but again, risky. So to convince my team, I made a little proof of concept prototype with 3JS, which was one of the ideas we actually pivoted away from in the end, but it kind of shows you, it kind of gets the idea across. So the goal of the visualization was to show our algorithm's footprint, you could call it, through the state space in such a way that anyone could really come in and get the gist of what's going on and, see the difference in scheduler behavior from one graph to the next. So what you're seeing here is the visualization for this graph. And it's been actually scheduled for 16, well, it's been allowed 16 logical processes, but I think it's only used 9 here. And see all the different schedules here and which task has been scheduled when. So this is actually a low density graph. The nodes here represent tasks and the directed edges represent dependencies between tasks. So in a nutshell, the solver essentially explores every possible partial schedule and relies on heuristics to prune back branches. So the visualization shows you the footprint of the algorithm through this potentially massive state space. The rings here represent tasks, so there are 16 tasks to schedule. Each line, so here, is a partial schedule the solver has picked to walk down that path. You can see here the solver picked this path, and then it's explored all these different paths. And the quote-unquote like refraction of the line is determined by a 52-bit integer hash of the partial schedule, which makes this actually completely deterministic. Same input will always get you the same output, or the visualization in this case. So here, the red and blue are the minimum and maximum angles of refraction, you could call it, and the hash actually determines the exact angle between those minima and maxima. So let's actually run this on a few more complex graphs, like this one. And if we just run this command, now you might notice that the visualization looks a little bit different to what I demoed last time in front of the lecture hall. And that's because there's been a few optimizations that have been made. The original idea that I mentioned earlier was to make this a sphere in 3JS, but even in like 2D, it struggled quite a bit with only a couple million lines being drawn. So the circles, each of these circles have actually been divided into fixed length arcs, where only one line can exist within any given arc. So if a given line starts a little too close, let's say this line starts a little too close to pre-existing line, then it would actually just reuse that pre-existing line without drawing over it. And that's mainly to deal with like the middle sections here, where originally that would have just been colored in and there have been so many lines being drawn over each other that wasn't really necessary to convey the point of like there's a lot of schedules being explored here. And of course, the resolution of those fixed length arcs, or the length, I guess, of those fixed length arcs decrease as we move outwards toward the larger rings to ensure, that we aren't getting massive gaps here, which isn't the idea. So that was a very condensed overview of how the visualization worked, and thank you for listening.